Hi, I'm Graham Lewis, and in this short video we're going to look at the goodness of fit chi-squared tests. There's actually three chi-squared tests, one for homogeneity, one for independence, and one goodness of fit. All of them have exactly really the same mechanics, so if you understand the mechanics of goodness of fit, you can do the other two. In another video, I'll explain the subtle differences of the other two. So I got this from the great AP Statistics book, Bock et al., Modelling the World. Does your zodiac sign predict how successful you will be later in life? Fortune magazine collected the zodiac signs of 256 heads of the largest 400 companies. The table shows the number of births for each sign. We can see some variation in the number of births per sign, and there are more Pisces. But is that enough to claim that successful people are more likely to be born under some signs than others? So let's have a look. So for instance, I'm a Gemini. So you can see that there's only 18 which is the minimum, like Libra. So does that mean I'm less likely to be a great company head? So let's have a look at this statistically, and I'm sure you're imagining a hypothesis test is coming up. So we should always, before we do an hypothesis test, we should always look at the data. So draw a picture. So this is my rather messy picture, my bar graph of the distributions. And you can see that I've put a dotted line for the mean, 21.33. So if we take all of them and add up and just divide by 12, assuming it's uniform and there's no difference, we'd get that. So you can see that me as a Gemini are a bit lower, and you can see that Pisces are a bit higher here. So always draw a picture first, and then we'll set up the hypothesis test. So a hypothesis test, null hypothesis, H0, is, let's imagine that, and we'll say that births are uniformly distributed over the 12 star signs. So what we're saying there is that if there's no difference in star signs, then there should be 21.33 company leaders in each month, or each star sign, sorry, the 12 star signs. The alternative hypothesis, which you can call HA or H1, is the births are not uniformly distributed over the 12 star signs. And we'll identify the test. We're going to perform a chi-squared test, chi-squared goodness of fit test, and we'll choose our alpha level of 5%. Before we go further, I just want to point out that the chi is a Greek letter. It's spelled C-H-I, but it's pronounced chi. Now we have a new test statistic for this called T, as usual, a test statistic, which is the sum of the observed actual number minus what you'd expect to get, square that to make them all positive, and then find that relatively to what you would expect to get. So that's the test statistics. And then we have a whole new distribution, like we had a whole new distribution for sample means for the T distribution, and we have now chi distribution, and it comes with a degree of freedom. Now here's the chi-squared 1 distribution. It's extremely positively skewed. Let's have a look at some other chi-squared distribution. So here you can see the very skewed chi-squared 1 distribution, and here's chi-squared 3, which is getting less positively skewed, chi-squared 7 with 7 degrees of freedom, even less positively skewed than chi-squared 3. You have very fat tails. It's always positively skewed, but guess what happens as the degrees of freedom increases? It tends towards a normal distribution, which is another amazing fact. Let's have a look at the assumptions and conditions to check that we can use a chi-squared test. Okay, so the assumptions and conditions for any chi-squared goodness of fitness test. So we have to have counted data. We do have counted data in each category here, for we're counting people in star signs. Independence. I think it's fair to assume that the birth date of one executive is independent of another. Randomization. This is a convenience sample, so we don't know how the data was collected, so we'll proceed with caution there. And then this is a really important one, this fourth one, the expected cell condition. Now the expected cell is what we would expect to get under our null hypothesis. So in this particular example, we're assuming a uniform distribution. So that means that we would expect to get the total number of executives divided by 12 star signs coming out at 21.33 recurring. So 21.33, that's the expected number in each cell, and that's bigger than 5, so we're okay. Now if it was less than 5, so for example Gemini was only 3, then what we'd have to do is actually add Gemini to one of the other star signs and combine the categories, because we cannot proceed if the expected cell is less than 5. Some people get confused by this and confuse it with the observed. We're not saying the observed have to be at least 5, we're saying the expected have to be at least 5. And when we come to the other tests, they won't all be uniform. There'll be different numbers in there. So just bear that in mind too. Okay, let's do the mechanics. Okay, here are the mechanics of a chi-squared test. So the test statistic, chi-squared, is the sum of the observed minus expected, all squared, divided by the expected. So for the first one, we had 23 observations. We minus the expected. We're considering every one is uniform, so 21.33, and we square that and divide by 21.33. So let's just scroll up to the table and show where those numbers came from. So going back to our original data, you can see the observed for Aries was 23. If we're assuming in H0 that they're uniform, so if they were uniform, we'd expect to get 21.3333. So we do 23 minus 21.3333 all squared divided by 21.333, and then plus, and we do it for each one of them, which is really tedious and boring. But guess what? We have computers for this kind of thing. So this is the kind of working that I would like you to show, and this is consistent with what is required on the AP examination as well. So obviously show the chi-squared, the test statistic. Always write down the formula, the sum of the observed minus the expected all squared divided by the expected, and then show at least 3 of the observations. So 23 was Aries, the first one, minus 21.33 all squared divided by 21.33 plus, and then the next one, whatever star sign that was, observed 20 minus 21.33 squared divided by 20.3, and then the third star sign 18, and so on, and put plus dot dot dot. Okay, so sometimes it's actually quicker to do it by hand if you have a very small amount of data, and sometimes it's quicker to enter all of the data into your TI calculator or use a computer software. Whichever way is quicker, do it the most efficient, but you must show this working. So I used my TI and I got 5.094. So now let's see how we can finish this test off and see if that's a significant result or not. Hi, so always draw a picture. So I've drawn a chi-squared distribution here, and you'll notice that in the calculator I've put 11 degrees of freedom. That's because we had 12 months, and so we do 12 minus 1, and we have 11 degrees of freedom. So we want to find the p-value, which is the probability of the chi-squared being greater than our test statistic of 5.094. And so we do chi-squared, we use the cumulative density function on the calculator, we enter the test statistic, enter a big number. I did 9,999, that's kind of representing infinity, and then put a comma, and the degrees of freedom is 11. And I get 92.6%, which is a huge probability. So we failed to reject H0 because clearly that's very likely. So there is no evidence to suggest that executives do not follow a normal distribution, a uniform distribution. Okay, so that's chi-squared in a nutshell. And so now I would encourage you to try a question for yourselves. So here's a question you can have a look at. So here's a question that I got from Bock et al., Modelling the World, the great AP Stats book. So birth month may not be related to success as a CEO, but what about on the ball field? It has been proposed by some researchers that children who are the older ones in their class at school naturally perform better in sports, and that these children then get more coaching and encouragement. And so does that actually make a difference in the professional level in sports? So what we have here in ball player counts is people born in January from a professional ball player was 137, 121, 116, 121, 126, and so on for the 12 months. However, we're not going to assume that it's uniform this time. We're actually going to do a goodness of fit test with the national birth population, because some people are more likely to be born, you can see, from months 7 to 12. So what we're going to do is find out the total number of the ball players and compare those to 8% being born in January, 7%, etc. So you can see here that we can get the expected count. So you can see here, if you add up together all of the number of ball players, you get 1,478. And so that if we take 8% of the 1,478, we'd get an expected 118.24 baseball players. Now leave those expected counts as decimals. That's fine. That's just saying what we would expect. The observations will always, if they're people, be counts and always be whole integers. But the expected can be decimals. And then I want you to go ahead and try this and do a chi-squared goodness of fit test. Is there evidence to suggest that the month you were born in, i.e. being older, is an advantage for professional ball players? Thanks very much for watching. If you like this video, give it a thumbs up and please do subscribe to my channel.